Mechanical ventilation is the use of a machine called a ventilator to help move air into and out of the lungs. This process supports or completely takes over the breathing function to ensure adequate oxygen delivery and carbon dioxide removal. Mechanical ventilation alone does not treat or reverse the underlying pathology leading to the need for ventilator support. Rather, it is applied as one of the support systems until the reversal of the pathological condition. Though there are myriad causes that necessitate mechanical ventilation, the three underlying reasons why mechanical ventilation is indicated are inadequate oxygenation, inadequate ventilation, and airway protection. Every pathology affects one or combinations of these three physiological requirements. Inadequate oxygenation, or hypoxia, results from conditions that affect the lungs' capacity to transfer oxygen to the tissues, mostly as a result of lung pathologies outlined here. This can be grouped as hypoxemic respiratory failure or lung failure. Inadequate ventilation results when the body is unable to eliminate carbon dioxide, leading to hypercapnia. Obstructive lung diseases like COPD, bronchial asthma, and emphysema are diseases that can lead to hypercapnia. Additionally, neuromuscular diseases such as myasthenia gravis, Guillain-Barré syndrome, and poliomyelitis can lead to inadequate ventilation. These conditions can be grouped as pump failure. Airway protection is an indication for intubation and thus also an indication for mechanical ventilation, as patients who are unable to maintain their airway need mechanical support until the underlying causes are reversed. Such conditions include traumatic brain injury, general anesthesia, and intoxication. Apart from these physiological derangements, there are also physiological parameters that need to be considered when planning for mechanical ventilation. These parameters include ventilatory parameters such as tidal volume, vital capacity, respiratory rate, and blood gas analysis parameters such as pH, partial pressure of oxygen, and partial pressure of carbon dioxide. Other parameters to consider are as simple as deteriorating Glasgow Coma Scale and oxygen saturation. The two major types of mechanical ventilation are negative pressure and positive pressure ventilation. The main form of mechanical ventilation is positive pressure ventilation, which works by increasing the pressure in the patient's airway and thus forcing air into the lungs with the help of ventilator which pumps the air into the lung. Less common today are negative pressure ventilators, for example, the iron lung, which creates a negative pressure environment around the patient's chest, thus sucking air into the lungs. Another way to classify mechanical ventilation is taking into account the invasiveness of the ventilation. Mechanical ventilation is termed invasive if it involves an instrument to create an airway that is placed inside the trachea. This is done through an endotracheal tube or nasotracheal tube. If tracheal instrumentation is not done, it is termed non-invasive ventilation. Negative pressure ventilation is a non-invasive ventilation. Positive pressure ventilation can also be non-invasive. Example of such is CPAP. We shall discuss these in detail after going through the mechanics of breathing first to understand the concept behind mechanical ventilation. Spontaneous ventilation or spontaneous breathing is simply the movement of air in and out of the lung. The main purpose of this is to bring in fresh air for gas exchange into lungs and to allow exhalation of air containing carbon dioxide. Inspiration is accomplished by the extension of thorax or chest cavity. It occurs when the muscle of inspiration contracts. During contraction, the diaphragm descends and increases the vertical size of the chest cavity. The external intercostal muscles contract and raise the ribs, thereby increasing the circumference of the thorax. The activity of these muscles represent the work of breathing. Exhalation is a passive process and doesn't require any work. The muscles involved in inspiration relax, the diaphragm relaxes and moves upwards to its resting position, and the ribs return to their normal position. The volume of the thoracic cavity decreases and the air is forced out of alveoli. Basic concept of air flow is that, for the air to flow through a tube or the airway, the pressure at one end of the tube should be higher than the other. Air always flows from higher to lower pressure due to the pressure gradient. Similarly, in the conductive airways of our respiratory system, the air flows from the mouth and nose and ends at the small airway near the bronchioles. The pressure in the alveoli is always lower than in the mouth and nose during inspiration. Conversely, during expiration the pressure in the alveoli is higher than in the mouth or nose. When the pressure in the alveoli and mouth are the same, as occurs at the end of inspiration and at the end of expiration, no gas flow occurs. This is because no pressure gradient is generated. The pressure in different parts of our respiratory system are different, and these differential pressures generate pressure gradients to ensure gas flow. Let's look into the individual pressure first, and later we will talk about the pressure gradient between them. Airway opening pressure or mouth pressure is the pressure at the mouth or nose of an individual. Also called airway pressure, the pressure is zero or atmospheric unless positive pressure is applied at the mouth or nose. Body surface pressure is the pressure exerted at the body surface. This is equal to zero unless the patient is using a pressurized chamber like hyperbaric chamber or negative pressure ventilator like iron lung. Intrapleural pressure is the pressure in the potential space between parietal and visceral pleura. Normally, the pressure within the pleural cavity is slightly less than the atmospheric pressure, which is known as negative pressure. This negative force acts as a suction to keep the lungs inflated. The pleura is inactive in terms of pressure generation. Therefore, the pressure inside the pleural cavity is a result of external forces affecting the parietal and visceral pleura. The elastic recoil of lung tissue and the surface tension on the alveoli causes the visceral pleura to be pulled inward. On the other hand, elastic pull by the thoracic cage causes the parietal pleural to be pulled outward, causing pleural space volume to increase. This reduces the pressure inside the pleural space according to the pressure-volume relationship of the Boyle's law. Alveolar pressure, also called intrapulmonary pressure or lung pressure, is the pressure of air inside the lung alveoli. The pressure within the alveoli of lungs is affected by the same force that affects intrapleural pressure, that is, elastic recoil of lung tissue and the surface tension and the outward elastic pull by the thoracic cage. Differences between the pressures we discussed earlier are called pressure gradients. There are three key pressure gradients involved in the mechanics of breathing. They are the trans-airway, transpulmonary, and the transthoracic pressure gradients. Trans-airway pressure is the pressure difference between airway opening and the alveolar pressure. It produces movement of air in the conductive airways of the respiratory tree. It represents the pressure generated by resistance to air flow in the airway. Transpulmonary pressure or transalveolar pressure is the pressure difference between alveoli and pleural space. It is the pressure required to maintain alveolar inflation and is therefore sometimes called the alveolar distending pressure. All modes of ventilation increases transpulmonary pressure either by decreasing intrapleural pressure as in negative pressure ventilators, or by increasing alveolar pressure as seen in positive pressure ventilators. The transthoracic pressure gradient is the difference between the pressure in the pleural space and the pressure at the body surface, and represents the total pressure required to expand or contract the lungs and chest wall. Together, the transairway pressure and transthoracic pressure is called transrespiratory pressure. It is the combined pressure required to overcome elastic recoil of the lungs and chest wall and the pressure required to overcome airway resistance. We will look into them when we discuss lung characteristics. Though complex, let's briefly try to understand how the pressure gradients acts during normal breathing. Before inspiration begins, the pressure in the pleural space is -5 centimeters of water as a result of the elastic recoil of the lung and the chest wall we studied earlier. The alveolar pressure is at 0 centimeters water, which is in equilibrium with atmospheric pressure or airway opening pressure as there is no gas flow. This translates into a transpulmonary pressure gradient of +5 centimeters water when the lung is in a resting state, that is, at the end of expiration. This pressure gradient helps to maintain the FRC or keeping the alveoli distended. As inspiration begins, the muscles of inspiration work to expand the thorax. Thoracic cage expansion pulls parietal pleura outward, further reducing the intrapleural pressure. As the pleural pressure drops, the transpulmonary pressure gradient widens, causing the alveoli to expand. As the alveoli expand, alveolar pressures drop below mouth pressures. Hence, pressure gradient between the mouth and the alveoli called transairway pressure is generated, causing air to move from the mouth to the alveoli. As pleural pressures continue to decrease toward the end of inspiration, alveolar pressure begin to equilibrate with the atmosphere and alveolar filling slows. At end inspiration, the transpulmonary pressure gradient reaches its maximum of about -10 centimeters of water as interpleural pressure becomes more negative. Normally, expiration is a passive process. Alveolar pressure becomes positive and higher than atmospheric pressure because the elastic forces of the lungs compress the greater volume of air in the alveoli. When alveolar pressure increases above atmospheric pressure, air flows out of the lungs and the volume in the lungs returns to FRC. All volumes and pressures return to their values at rest and the system is ready to begin the next breathing cycle. The volume in the lung during the end inspiration is the tidal volume and the residual volume together. At the end of expiration, what is left inside lung is the residual volume that keeps the alveoli inflated. Two types of forces oppose inflation of the lungs. These are the elastic opposition to expansion of the lungs and the frictional opposition to air movement. The pressure change that is generated on inspiration must be sufficient to overcome such forces. The effort required to overcome this opposition to lung inflation is termed the work of breathing. Physical resistance to gas flow arises due to friction between gas molecules against the walls of airways, that is, airway resistance, and due to the friction between the tissues of the lung and the chest wall, which is called viscous tissue resistance. As the lungs and thorax move during ventilation, the displacement of structures like lungs, diaphragms, rib cage and abdominal organs creates resistance to breathing. Such tissue resistance, called viscous resistance, remains constant for an individual under most circumstances. For example, obese patients will have increased tissue resistance, but it doesn't change significantly when the same person is mechanically ventilated. So during mechanical ventilation, we are concerned more about the resistance caused by conductive airways. Certain equations can be used to determine airway resistance. Ohm's law usually refers to electrical circuits, in which current is equal to voltage by resistance. However, it can also be applied to describe the relationship between airflow pressure gradient and resistance. The equation is, flow is equal to pressure gradient by resistance. This demonstrates that as resistance increases, the pressure gradient must also increase to maintain the same rate of flow into the alveoli. The resistance to airflow through the conductive airways also depends on the gas viscosity, the gas density, the length and diameter of the tube or airway, and the flow rate of the gas through the tube, as defined by Hagen-Poiseuille law. This law was discussed in depth in flowmeter physics in anesthesia machines. The link is provided in the description. Finally, if we combine these two equations, we can determine the factors that affects the flow through our respiratory system. And, since flow is inversely proportional to the resistance, we can also determine the resistance. So what is the significance of all these equations? In clinical situations, the density and viscosity, and the airway length remains fairly constant. Other parts of equations will be constant too except for the radius or the diameter of the tube. With an artificial airway in place, resistance can increase depending on the size of the endotracheal tube. The diameter of the lumen and the flow of the air will decrease as a result of bronchospasm, secretion, mucosal edema and kinks in the endotracheal tube. With higher resistance, more of the pressure for breathing goes to the airways and not the alveoli, and with less pressure in alveoli, a smaller volume of gas is available for gas exchange. On the side note, changes in airway resistance can be visually observed on a ventilator system using the pressure-volume loop display. An increase in the bowing of inspiratory or expiratory curve or both depending upon the direction of the bowing of the pressure-volume loop suggests an overall increase in airflow resistance. Modern ventilators can also analyze ventilator flow, volume, and pressure to calculate the resistance with this formula. More will be discussed about this in ventilator graphics section of the playlist. The elastic forces are encountered as a result of both the lungs and chest wall being elastic structures. When they have been inflated or deflated, they tend to return to the same resting position of equilibrium once the driving force has been removed. The lungs naturally want to collapse and the chest wall naturally to expand. Thus, each exerts a pull on the other. Pulmonary physiology uses the term compliance to describe this property. So, compliance is the relative ease with which the structure distends. Mathematically, compliance is change in volume over change in pressure inside the lung or transpulmonary pressure. Therefore, compliance of the respiratory system is the sum of the compliances of both the lung parenchyma and the surrounding thoracic structures. Low compliance means the lungs are stiff or non-compliant, making lung expansion difficult and increasing the work of breathing. For example, in lung fibrosis. High compliance means that there is incomplete exhalation, air trapping, and reduced carbon dioxide elimination due to a lack of elastic recoil in the lung as seen in emphysema. For a typical lung at functional residual capacity, compliance is about 200 milliliters per centimeter H2O. The compliance of lung can be divided into static and dynamic compliance. Static compliance describes pulmonary compliance when the patient is not breathing or when there is no airflow, like an inspiratory pause. This is defined as the change in lung volume by the change in pressure, in the absence of flow. It relates to the elastic resistance of the lung and the chest wall. Dynamic compliance describes the compliance measured during breathing, which involves a combination of lung compliance and airway resistance due to the flow of the air. It is defined as the change in lung volume by the change in pressure, in the presence of flow. By including airway resistance, it is therefore always lower than static compliance. This is because the pressure required to inflate the lung is used up, overcoming the resistance to the airflow. Static and dynamic compliance can be represented graphically with a pressure-volume loop. We will briefly try to understand it. The diagram given here is called a compliance curve, where the top curve represents expiration, and the bottom curve represents inspiration. The path or slope of this curve represents dynamic compliance of the lungs as these are plotted during the airflow, or while breathing. And, because these curves are the dynamic representations of breathing, there is resistance both during inspiration and expiration. The space between the curves represents the resistance. In other words, the space represents the energy needed to overcome inspiratory or expiratory resistance, which is termed work of breathing. Static compliance is represented by the linear dotted line joining the end inspiratory and end expiratory points of the compliance curve because there is no air flow during that time. Once again, the detailed dissection of pressure-volume loop will be carried out later in the ventilator graphic series. Static and dynamic compliance can be measured by measuring the tidal volume and the pressure generated by that volume. For that, we need to get the value of pressure generated when there is air flow to calculate the dynamic compliance. Similarly, we need to get the value of the pressure generated when there is no flow to calculate the static compliance. We can get that value from the pressure time scalar, which represents the pressure in the airway as a function of time. The pressure time scalar starts at end expiration when the lung still has air, and thus pressure inside it. This pressure is called positive end expiratory pressure, which is the pressure applied by the ventilator at the end of each breath to ensure that the alveoli are not so prone to collapse. As the inspiration begins, the pressure increases and reaches its peak at the end of inspiration. This pressure is called peak inspiratory pressure, which is the highest pressure generated by the ventilator to overcome both airway resistance and elastic resistance. So, peak inspiratory pressure is used to calculate dynamic compliance. Now, to simulate the scenario where there is no air flow, we can perform the maneuver called end inspiratory pause on the ventilator. The pressure then suddenly dips as the flow of air is stopped, excluding the resistive part of air flow. This also means that airway resistance no longer plays a part in pressure generation. The reduced pressure is called plateau pressure, which represents pressure due elastic nature of lungs, and is used to calculate static compliance. Lastly, as the expiration begins, the pressure further drops to its positive end expiratory pressure as the lung volume decreases. So, what is the significant static and dynamic compliance? Well, there are conditions that affects either static or dynamic compliance. We just have to know that conditions that affects only lung elasticity leads to changes in static compliance, and conditions that affects conductive airways disturbs dynamic compliance. We are going to revisit this concept during peak and plateau pressure lecture. The compliance and resistance that we have studied varies throughout the lung. Thus, the characteristics of lungs are heterogeneous and not homogeneous. Time constant basically describes how rapidly those heterogeneous lung units fill and empty. Let's take an example of two lung units, A and B, for comparison. In this diagram, both lung units have equal compliance and resistance, and therefore fill at equal time. In this illustration, lung unit B has narrow airway which offers more resistance to the air flow. So, it takes longer to fill. Here, lung unit B has lower compliance than unit A, therefore it fills up at same time as unit A but incompletely. This is because lung unit B has the reduced ability to stretch or distend. And here, lung unit B has both lower compliance and higher resistance. So it takes longer time to fill and also fills incompletely. Basically, the implication of all these diagrams is that lung units with different time constants will fill at different rates and potentially also up to different final volumes. So, time constant is a single parameter that can tell us about the overall respiratory characteristics encompassing both elastic and airway resistance. It is measured in seconds and is a product of compliance and resistance. Time constant or one-time constant is the time required to fill or empty 63% of the lung unit. Two-time constants fill 86% of the lung unit and three-time constant fill 95% of the lung unit. At the end of five-time constant, the lung is said to be 100% full. This happens when the lung is free from any disease condition. For normal lungs with a total compliance of 0.1 liter per centimeter water and airway resistance of 0.5 to 2.5 centimeters water per liter per second, time constant is 0.1 second. If you recapitulate the illustrations of time constant discussed earlier, we know that poor compliance units will have a shortened time constant, and will fill rapidly but incompletely, and high resistance units will have a long time constant, and will fill slowly. Obviously, if the inspiration is very rapid, the only units which are completely filled are going to be the units with the shorter time constant called fast alveolus, which are going to be probably the poorly compliant units. Then, when the inspiratory flow stops, the lung units with longer time constants, usually described as slow alveoli, will continue to fill with borrowed gas which redistributes from faster alveoli. The two time constants, inspiratory and expiratory time constant, helps decide the inspiratory and the expiratory time on the ventilator.